Good afternoon. Good morning to some of you, and like those from East Western Canada, and good evening to those participating to these sessions from other parts of the world. My name is Ali Asghari. I'm professor of disaster and emergency management at York University, and currently serving as CIFAL York director. I would like to officially open this speaker series with the first session coming shortly with a quick land acknowledgement. York University recognizes that many indigenous nations have long-standing relationship with the territories upon which York University campuses are located, and that precede the establishment of York University. York University acknowledges its presence on the traditional territory of many indigenous nations. And I would like all of us to recognize that, whether you are at York or any other parts of Canada. With that, I would like to mention that this speaker series tries to bring together experts from national and international levels, and from different sectors, private, public, academia, and NGOs, to share their knowledge and expertise around one of the most critical and important aspects of disaster and emergency management, that is rapid response, rapid damage assessment, basically, which, of course, has a lot of implications for disaster response and recovery. And that is why CIFAL York, with collaboration with other agencies, in this particular case, is interested in pursuing this very important aspect of disaster and emergency management. We have currently organized 4 sessions for this speaker series and hope to possibly extend it beyond 4 and go to an additional probably 2 sessions in the new year. Before we begin, I would like to introduce our representative from the city of Calgary, who was basically the driving force behind this speaker series, bringing the idea and its importance and willingness to participate, and also collaborate with us on developing this speaker series. Hadia is a business continuity and emergency planner with the city of Calgary. And she joined the city in 2014. I should mention that she was one of our graduate students in disaster and emergency management at York University. We are very happy to see her contributions to this field, and professionally as well as academically. She's now leading emergency and continuity management program for planning and development services department in the city of Calgary. In the past 3 years, Hadia was heavily involved in redesigning the rapid damage assessment process for the city, and is very excited about her these speaker series, and we really appreciate her contributions and her involvement and idea on this. She is going to briefly welcome participants and also provide you with some background about this speaker series. Hadia, please. Thank you.
Thank you, Ali. Hello, everyone. As Ali mentioned, and thank you so much for the introduction, Ali. So I'm Hadia, and I'm very passionate about this topic. It's been 3 years since I learned about rapid damage assessment and what it takes and what are the results and outcomes of rapid damage assessment and why it's important in this industry. As Ali mentioned, I am a graduate from York University in disaster and emergency management, and it's been about 10 years that I'm a professional emergency planner and working in this field as a professional, but still trying to contribute a bit to the academic part of it as well. So the whole idea, of course, came from relooking and redesigning our rapid damage assessment process at the city of Calgary. And with organizational changes, of course, we always think about changing our processes and making them better and better every day. doing a little bit of literature review across in Canada and in North America, basically, I realized there's not a lot about the rapid damage assessment. Not a lot of heavy and reliable literature about it. So I actually reached out to Ali, and just because Ali is my great professor, just talked about this topic. And then we thought we could have some speaker series and have some great people like yourselves attend and talk about your experience. So I'm so excited about this today. It's going to be a lot of learning for me, and I'm sure a lot of us will be enjoying the conversations today. And I'm very much looking forward to this. Thank you so much.
Thank you very much. Thank you. Now, before and without any further ado, I would like to introduce our first speaker for this series, and that's Dr. Hamad Imran. He's a senior scientist and lead of the crisis computing team at Qatar Computing Research Institute. His interdisciplinary research focuses on natural language processing, social computing applied machine learning, human-computer interaction, and stream processing areas. He analyzes social media communications during time-critical situations and disaster and emergency-related issues using big data analytics, such as data mining, machine learning, and deep neural network. He develops novel computational models, techniques, and technologies useful for stakeholders to gain situational awareness and actionable information during sudden onset disasters, which is very important for this topic and speaker series that we have. Dr. Imran received his PhD in computer science from the University of Toronto in 2013. He then joined Qatar Computing Research Institute as a postdoctoral researcher. Dr. Imran has published over 90 research papers in top-tier international conferences and journals, and I encourage everyone to visit later on his list of publications that are really important in our field, from technical and also professional perspectives. Lots of journals, of course, to name. 4 of his papers received the Best Paper Award and 2 Best Paper Runner-Up Award. He has been serving as a co-chair of the Social Media Studies track of the Information Systems for Crisis Response and Management International. That is a community organizing also international conference. He has been co-chairing this since 2014 and has served as a program committee for many major conferences and workshops. It's a great pleasure to have you, Dr. Imran, with us today, and looking forward to your presentation. Definitely, this is of interest to all of us. And I just want to, before we begin, I want to mention that we have a list of speakers. Each of them will talk about different aspects of rapid response. Our arrangement of speakers for this series is not based on a particular theme. It's mostly based on their availability. So coming to this speaker series, all of them, you will be able to get, knowledge and information about various aspects of this when you put all of them together. Thank you very much again, Dr. Imran, and I stop here and floor is yours. Thank you.
Well, thank you very much, Professor Ali. Let me share my screen. So I hope you can see my screen. Well, good morning, good afternoon, good evening, everybody. My name is Hamad Imran, and today I'm going to talk about the role of AI and non-traditional data sources for rapid damage assessment. So before I start getting into the work that we are doing at QCRI, I want to discuss and make some argument here using this diagram. So there are mainly 2 things that I want to talk about here. One is why timely decisions are important right after a disaster, and then what is the current state of response as of today. So on this diagram, if you see, the x-axis represents the time, and the y-axis represents either the impact of a disaster or the effort in terms of response. And the red line here shows the, the disaster impact when it occurs, and then the blue line shows the response. And in between, you see there's a gap, and the community harm represents that gap. So what happens is, due to the delayed access to information right after a disaster, that leads to delayed decision making, and that leads to definitely delayed actions and high community harm. So at Qatar Computing Research Institute, our target is to bridge this gap, to provide humanitarian organizations the kind of information that they need to expedite their decision-making processes that leads to rapid actions, and eventually you expect low community harm. So to further make this argument more stronger, this is a diagram that shows the result of a large-scale survey done by FEMA in the US. And they interviewed many disaster management officials, and they asked about the value of different types of information for first responders right after a disaster. And these information, as you can see, in terms of building damage information, communication network damage information, transportation damage, damage to critical infrastructure, and so on and so forth. Now, the main thing here is that you see as time passes, the value of different types of information on this plot reduces, right? And you see that, for example, after 24 hours, the value of building damage reduces 10%, and after 48 hours, it reduces even lower than 70%, and so on and so forth. So this indicates that each passing minute is very valuable, and that also, if the information access is hindered by any means, that leads to poor disaster response in terms of from the first responders. Now, we try to develop technologies, and we try to target this first 24 to 48 hours, and we try to access information, compile that information, and provide that information to different humanitarian organizations so that they can do better decision making and then take actions accordingly. Now, the data sources is one of the fundamental piece here. So no technology can work without the data, and once you have the data, you apply algorithms, and then you actually get early warnings, or you assess the impact of a disaster, and so on and so forth. Now, we try to take a different route in terms of data sources, and we go towards unconventional data sources. And here I mean social sensing data, and that is mainly coming from social media sources. And that hundreds and thousands of millions of users are using different social media platforms like Facebook, YouTube, Instagram, Twitter, and so on and so forth. And these are the sources. We consider them as a real-time data sources, data coming from mobile devices of the users who are on the ground, are near to the disaster impact areas, taking pictures, posting about their statuses, and so on and so forth. So we want to leverage on this information. So when we started actually building technologies, or thinking to do, to build assistive technologies for humanitarian organizations, we wanted to see what kind of information come on social media and who actually shared this information. So we analyzed a large number of disasters data from Twitter. Here it's a partial view of that analysis. We, in fact, analyzed 13 different disaster events all over the world, over 100,000 tweets, and we wanted to see two things. One is, what are the different types of information that people share, and who is sharing that? So the blue circles here are the sources, and the gray circles here represent the types. And you see, among many other things, the people share, the needs, their urgent needs, and then also the donations that they want to offer. And then the tweets, messages contain affected individual, injured people reports, missing people reports, and so on and so forth. But what is most important to this session and us as well is about the reports pertinent to infrastructure damage and utility damage, and so on and so forth, different types of impact. And in terms of who are these, who share this information, you see that although the distribution of eyewitnesses in different disasters is different, but there was 39% of the information that we assessed came from eyewitnesses in Manila floods in the Philippines. And in general, there was a substantial amount of information that we analyzed came from the general public. That was very, very helpful for us to, further, lay down a plan to utilize, first of all, collect this information from eyewitnesses, from general public, and extract the information about, damages, about needs, about affected people. So before getting into the technologies, I want to briefly share the types of data on social media. So basically, you see that there are three types of data that people share, on social media. One is this textual data, where people write about, if they need some sort of help, or they are offering some sort of shelters, or they are, providing warnings or cautions to other fellow citizens about some road closures and so on and so forth. And in terms of images, they share images of what they see in their streets, the houses nearby, and so on and so forth. And they also share, videos. But today I'm going to take a deep dive into the images, because that is the most important information that we can use to assess the damage, right? So this is the images that come from eyewitnesses, or information that come from the general public, are our primary data sources here to assess the damage. Now, you see, these are the real images taken during different disasters from Twitter. And you can see there are images about road infrastructure damage, images showing building damages, and images showing electric and telecommunication line damages. Now, what this social media, and in particular these images, provide in terms of advantages compared to other conventional or traditional data sources. So first of all, these are ground level imagery, as opposed to, for example, you fly a drone or UAV, or you rely on satellite imagery. And these images are coming from, eyewitnesses, and these are first-hand reports. And they are quickly available to you. Like within seconds, this information pour in. And if there are systems in place, you can, quickly leverage this information, turn into actionable insights. And, in terms of activation, social media, most of the social media data is available. Some offer APIs, some don't, but these are readily available. And most importantly, there's a variety of scenes, and there are a variety of information that these images, these scenes provide you, like in terms of infrastructure damage, or in terms of residential building damage, or maybe flooding, and so on and so forth. Now we know that social media could be a potentially useful source of information, but as with other, data sources, social media has its own challenges. So what are those challenges? So first of all, social media, in particular Twitter, give you very high volume of data in a very, shorter temporal boundary. So here there are numbers from some old disasters, like you see tens of millions of images or tweets, posted during these disasters. And these are, these give you a flavor of big data, where the volume is very high in a very limited time window. Not only that, the velocity of this information on social media is very, very high as well. So for example, during a Japan earthquake, there were 60,000 tweets per minute posted. And you see that the gray lines also represent some other events on social media where there are 100,000 tweets were posted per minute, and so on and so forth. So with this high volume and high velocity, despite you have a large crowd of people to analyze this data, this is beyond their capacity. And that, for that, you need to have some assistance from machine. So in addition to these two challenges on social media, you must have noticed that the social media is a very noisy data source. And there are, although you collect data during disasters and you expect that the data will come cleaner, but these are the images. These are the real images we collected during disasters, and yet they are totally irrelevant. And in our experience, almost 60% of the information or the images that we collect during any disaster are totally irrelevant to the disaster. And these are the scenes of advertisements, celebrities, and whatnot. Additionally, the fourth challenge that we see using social media data is, there is a high redundancy. Like people reshare, retweet information, and that becomes a challenge. So there is a almost 80% of the times the data point that we analyze is a duplicate data point. And in terms of images, you can have a blurred version or unblurred version of the same image, or an image with and without text, or maybe a cropped version of the image or resized version of the image. Now, what it leads to, although these images are all probably relevant to some emergency response functions, but when we give this duplicate content to decision makers, this does not add any information to them. So this just waste their time. So our now target is to identify if there are some duplicates, and discern that duplicate content from the stream, and only provide unique, useful, and actionable content to the stakeholders. Now, having those challenges in mind, the task that I'm going to talk about here is the damage detection and damage severity assessment. Now, the images that we collect from social media, we try to detect whether that image shows damage or not. And then we also try to detect the severity of the damage. So we have 3 levels of severity. 2 of them are the representation of the damage, the mild damage, and we define it as any infrastructure that is partially destroyed. Probably in terms of residential buildings, those are probably livable, are probably drivable roads, are probably drivable bridges. And the severe damage, we define it as fully destroyed buildings, roads, or bridges are more than 90% part of that building or road or any infrastructure. And we consider them, those are not anymore livable, are not drivable, and so on and so forth. So this is our definition of mild and severe here. And we try to, detect, first of all, the damage, and then detect the severity of that. Now, as I showed you earlier, that there is a high irrelevant content on social media. So based on our analysis of past disasters. Here I'm showing you Hurricane Harvey, Hurricane Irma, and Maria, and the content of severe damage images, mild damage images, and images that show no damage. And you see that only 3 to 8%, the red portion of the bars represent severe damage. And you see that only 3 to 8% of the images that we collect represent severe damage. And in order to obtain this 3 or 8% of the data items out of millions of data items is a very challenging task. And we call it as a low signal to noise ratio stream that we have to process and extract these, diamonds in the rough kind of thing. And to do that, we have developed, a system which is an extension of our earlier system called AIDR. And this system is Rapid Damage Assessment, RDA system. And it consists of several components. Here I, showing you a very high level abstract, major components of the system. So the first component is called denoising component, and that mainly deals with the, irrelevant content. I showed you about the cartoons, the celebrities, and so on and so forth. And this is a deep learning model. In particular, this is a ResNet 50 model that we have fine-tuned fine-tuned on the images that we consider relevant and not relevant. And these are the, the numbers in terms of performance of this model, and these are pretty decent. Now, the second challenge, as I showed you earlier, that social media has high duplicate content due to resharing, retweets, etc. So we need to have some kind of deduplication process. And for that, we have, this deep learning based module that extract deep features from each image and builds a cache of all the images that we see from a given disaster. And each incoming image is then compared against that cache. And then we see whether an image is an exact duplicate or near duplicate, and so on and so forth. And even an image is near duplicate, we actually don't pass it to the next component and don't pass it to the officials. Now, the third and the most important component is obviously the damage detection and severity assessment, where actually, again, it's a deep learning model. And we have fine-tuned that model on, mild damage, severe damage images. And you see that there's these are the performance and F scores. And just to briefly highlight that, you see the system is not really confident about the mild damage category. And we actually figured out that even when you give one damage picture to 2 humans and you ask about their assessment of severe and mild damage, even though you have a very crisp definition of these mild and severe categories, there will be some subjectiveness, and they don't actually often agree to what category they want to assign. But anyway, so once the images are identified either as no damage, mild damage, severe damage, then we geomap them. We need to obviously see which street, which area the image is showing the damage. And then we also try to find the user type. And I showed you earlier that we are interested in eyewitnesses and general public. So once we have all these, computational processes finished, we have, mild and severe damages geolocated to areas of disaster posted from certain type of users. And we applied, this strategy to different, disasters in the past. And we have seen, very fruitful, very promising results. So here, for example, we applied this to an earthquake event in Italy. And you see that we filtered stream using the machine learning models, and this row represent, or this side represents the filtered version of only damaged images, and this represents the unfiltered, like the raw images that are posted from or around that area. And you see there's a lots of noise here, and after applying our models, there's a huge reduction in noise, and you have certain points in different within the proximity of the earthquake, which actually show promising results. So you see that the filtered average precision of our data points is pretty high compared to the unfiltered one. So for example, 89% compared to 27%, and so on and so forth. These are for different events: Bangladesh earthquake, Chennai flooding, and Italy earthquake, and so on and so forth. So this was, there are a couple other experiments that we did to showcase the effectiveness of these models. Now, we also deployed this system during real-world disasters. Now, the whole aim of building this system was to deploy it during an ongoing disaster and extract mild and severe damages and give it to officials in real time. That was the purpose, right? So we joined hands with the Montgomery Community Emergency Response Team in the US during Hurricane Dorian. So FEMA was interested in, getting social media reports of damages. And they tasked this CERT community to go to social media platform, collect images that show damages, and then try to, provide that information to officials. So they actually approached us, and we deployed this system together with them. This is the page that we actually deployed for them, and they were accessing this page in real time as images come into the system, and we were filtering through this machine learning model and showing them whether it's a severe damage or not. So in total, we collected around 8 million tweets, and out of 8 million, there were 300,000 images during the whole duration of this Hurricane Dorian. And we also, these Montgomery volunteers or experts also analyzed a portion of our system predicted images as severe or mild damage. And I'm going to talk about that. How did we do that? So for that, we created this interface where we show an image of either damage or no damage, and whether it's a severe damage or mild damage. This was the interface for the experts in Montgomery community, and we highlight the system prediction. So for this image, the system says this is a damage, and this is a severe damage. Now the human looks at this, and then he or she can submit and agree that this is correct according to the system, or can change the labels. It can say, no, this does not look at severe damage, this is a mild damage. So that's how we analyzed around 30,000 images by the CERT experts during the deployment time period during Hurricane Dorian. And so these are a few distributions. Just to reiterate the point, the amount of irrelevant, you see that these are the image distributions over time from August 30th till September 14. The total data points, the irrelevant points in red, and the relevant points. The relevant points, the relevant images contain mild and severe damage. Now, the most important thing that I want you to pay attention to is this. As I was saying earlier, that the main point of the system is to reduce the huge burden on the experts while they are, bombarded by the social media in terms of millions of data points. So you see that although we collected around 300,000 images, we found that only 42% of them were unique, and only 27% over all the days were relevant, and 5% were mild damage images, and only 3 or 4% were severe damage images. So see the reduction from 300,000 to 11,000. This is a huge reduction in the information overload to those experts if there is no system in place. And this is beyond human capacity. All right, so here I show you some outputs of the system. So these are the system prediction where the system says the severe damage, mild damage, and the system said no damage. And these indeed look, very promising results. Now, the system is always not perfect, so it makes mistakes. And with the help of, as I told you earlier, that there were 30 experts analyzed around 30,000 images during the course of this deployment. And out of these human expert validation, we found that around 76% of the times our system was correct. That is basically out of 28,000 images, 21,000 predictions by the system were correct, but there were 6,000 images were not correct. And what are those images? So these are, here I put some examples. So these are the false positive images where the system is saying this is damage, but actually it is not damage according to the human experts that analyze these images. So indeed, these are not damage. So this is a pile of trash. The system confused it to, maybe debris, and then it says this is damage. So this is a wooden pathway. The system considers that this is a damaged pathway and says a damage, but according to human, it is not. And, this is the wood pieces, bark, and the system thought this is a damage, and so on. So there are some mistakes in the system that we, with the help of these, human assessment, we identified, and so on and so forth. There are also some false negative cases where actually the system was unable to detect as damage. So this was indeed a damage image, but the system said this is not damage. Similar here and here and here. So here we see that these are a little bit challenging cases. This is a low light case. And later on after this deployment, we identified that the system has a weakness to detect damages in low light scenes. And now we are, making a system, trying to overcome this weakness. So what actually we did, we actually took those feedback from the experts and retrain our system. So here are the, an overall picture of the two tasks, whether an image is damaged or no damage, and whether it's a severe damage, mild damage, and none. And you see that 21% of the time when the machine says it's damaged, the human says it's no damage. So these are the false positive that I was showing you earlier. And similarly for mild, there was confusion in the systems. And we try to, overcome that. And so some key, observations here that the models are more sensitive to detect damage. Probably it's overtrained for something. And that's the research that you do. So you try to deploy these things in the wild, and you try to learn the weaknesses, and you try to improve them over time. And that's what we are doing that. And in fact, we close the loop with the help of expert annotations, and we retrain our model, and we showed better accuracy. So here are the 4 models. The old model, this is the old model, but we tested on Hurricane Dorian. But then the 4th model represents when we combine old model training images with expert annotations that we just got during Hurricane Dorian, And we trained a model, and that achieved, better performance over all previous models. And that was really promising to see that not only, we help these officials during real disasters, but their feedback can help us improve our models, and we, make our systems ready for the future deployments. So this was another deployment, and here we actually deployed our system during Beirut explosion in 2020, where we analyzed 100,000 images right after that explosion took place. This was on the demand of UNDP, and we also geolocated these images, the reports that are coming from the city about damages, damaged building, and so on and so forth. And we identified that out of 100,000 images, there are 12,000 that show severe damage and 4,000 that show mild damage. Now, so far, I talked about, image level damage assessment. So given a full image, overall, what is the damage level? But right now we are doing, we are making progress on this research. And now our focus is to go from image to object level damage assessment. So for example, in this image, you see that there are different objects. So there is a vehicle here, there's a road, there is a bridge at the back, and there are buildings and so on and so forth. There are different objects. There's a person here as well. So we see that the image level, damage assessment is helpful, but for some emergency response functions, or some particular, departments in the response function, let's suppose transportation, or maybe the telecommunication department, they are interested in certain type of damages in certain infrastructure. So for example, only images that show roads, right? So that requires us to detect whether the image has road and whether it is damaged or not. So this is something we are doing now. For example, take this image where you have, a destroyed house on top of a car, and that car is also destroyed. And there are some people standing by, and there are some buildings at the backdrop. We applied different object detection models on this image and tried to detect whether these models are, performing any good. There are several open source object detection models people have trained over the years. And we just, before we start our research or put our resources into this direction, we wanted to see if these models are any good for, damage scenes. And unfortunately, we see that most of these models are not doing as expected, and either they are not able to detect the objects correctly, or they are not able to segment the boundaries of the objects, and it becomes very challenging. Here I show you one example. So this is the original image of a collapsed building on top of a car, and we gave this to the best model in the industry. And the model, see what the model is saying. This is saying this is sky. So the whole destroyed building, according to the model, is sky. And this is the pole. Okay, probably this is pole or tree. Probably this is pole. It detects building well, but it did not detect car at all. It did not detect the damaged building at all, and so on and so forth. In this image, there is a telecommunication pole or electric pole is destroyed. It's blocking the road. There is a truck which is upside down, and so on and so forth. And we see the detection of the models. The model actually did not detect this pole at all, and then it did not detect the truck at the back, and also the destroyed telecommunication lines. So after looking at these, results, we, try to initiate and collaborate again with these experts from Montgomery Community Emergency Response Team and try to, quantitatively understand what are the weaknesses of these models so we can, focus on addressing those weaknesses. And this is an effort that is ongoing. I don't have, models yet to show you the final output. Hopefully in 6 months or in few years time, we may have, robust models ready to be deployed during real world events. So towards the end, I want to talk about a few other initiatives. So for example, this is, we are going beyond detecting damages. Here, this is a collaboration with MIT where we are trying to detect different types of events like wildfires, car accident, earthquakes, flooding, and so on and so forth. And in different places, like in bridge, in farm, forest, gas station, highway, houses, ocean, and so on and so forth. So we have built a very large scale data set, around 1 million images that we hand labeled with places and disasters. So this is also some effort that is ongoing. And briefly, I want to mention another system that we have developed called Global Landslide Detector. This is, again, using social media images and try to detect whether the image shows landslide, rock slide, or mudslide. And this is a collaboration with British Geological Survey and European Mediterranean Seismological Center. And we're providing this data to them in real time for their, decision-making and response functions. Lastly, briefly, I want to show you other efforts that we're doing. So not only social sensing, we are trying to see the opportunities when we combine remote sensing and social sensing together. And we see the opportunities when we fuse this data from satellite and social media together, how this can help us. For example, you must have seen that using satellite, people can detect flooding or wildfire and so on and so forth. But what they lack in what type of impact a particular flooding or a particular disaster or an earthquake brought to the area. And that is something we actually try to understand from the social media. So although we learn that an area is flooded, we don't know the type of impact it caused. So that is something we learn from the images that people share from that area, and so on and so forth. So with that, in terms of conclusion, I want to say that although I try to convince you social media as an unconventional data source is very useful, but this is not a silver bullet. We always suggest and recommend to use it in addition to other signals, use it to triangulate with other signals and see if it can help you. And always, involve practitioners from early on when you're developing these models or when you are actually testing these models or fine-tuning these models. And obviously, the disaster landscape change over time. There are different phases and so on and so forth. So we need to have more robust models that understand the drifts, they understand the anomalies and the errors of different stages of the disaster. So we need to have, more human in the loop kind of systems where the system can adapt based on the situation and so on and so forth. And I always say that for social media researchers that they need to pay attention to the data that they use. So this is something like if you train your models on, some noisy data, so you expect noise and output. So you have to, trace the weaknesses of your data before you train the model and always do the error analysis. As I showed you during Hurricane Dorian, although we deployed those models in real time, we wanted experts' feedback to improve our model. So that's the kind of error analysis and feedback loop that I suggest always to have in place. So with that, as I showed you, there are different challenges that we're trying to address, like low light scenes, wide area scenes, and so on and so forth. And slowly we're making progress towards that. With that, I think I'm going to stop here. And thanks again. And I look forward to your questions.
Great, great. Thank you so much, Dr. Imran. It was very, very insightful and interesting presentation. I think you covered in 50 minutes or so everything in this area, what's the development and great works that you are doing in rapid disaster assessment using different data sources, especially social media. I think this was great. Thank you so much. Now we have some minutes for Q&A already. We have 3 questions, I believe, in the Q&A. You can probably read them yourself, but I'm going to read the first question from Steve Peterson that I believe you also quoted him in your presentation. If I'm not mistaken, it's of course could be different Steve, but Steve is asking a question. All right, let me read the question, but I would also probably I can possibly invite Steve to ask this question or follow-up question himself. So the question is, of course, he's also sharing the same observation about your presentation, finding it very insightful. Do you think experts globally could help your system in providing universal definitions for mild or severe damage? I believe countries have their own specific definitions that may differentiate from other countries. Any comments or response to this very interesting question, Dr. Imran?
Yeah, thanks, Steve, for the question. So definitely. So as I showed, and with like Steve Peterson has been really instrumental from Montgomery Community Emergency Response Team to help not only improve our models right during the disasters, but also during normal times we collaborate and always seek experts' opinion and their help in annotations, defining our taxonomies to build this model. So as one of my conclusion points was to always involve practitioners in the pipeline while you are developing the models or you are testing the models. And not only testing the models, you go beyond when you deploy the models in the wild. There, in fact, the opinion, the validation of experts would be more valuable because the kind of instances, the images that the system sees during deployment in the wild can never be seen during, in a controlled lab environment. So I guess, I think, yeah, this is having experts, is always helpful.
Thank you very much. I also noticed that Hedy has a question, and among the participants, we also have a question possibly from participants. Let's start with Hedy and go to Dr. Moshiri after that. Please, Hedy.
Thank you. Thanks, Dr. Imran, for a great presentation. Just a question, again, related to my job on my day-to-day thing. So what you presented is more on the community level and a town or a city level. My focus is at property level. So do you think the images and the models you're using could be used for property level assessment of damages? And how much details could they be capturing potentially?
So, so property level, what do you mean? Like you designate some So can you,
Yeah,
elaborate what you mean by
absolutely.
property?
So, I mean, the images, the example of the images you had were like a wider range image of like an aerial image from for a wider range, or I would say a surface. What I mean by property level is like, let's say a drone going down at a property like at a house level goes around the house and take images of one property at a time, just to get an extent of the damage of that single property.
Sure. Yeah, this is a very good question. And in fact, this is linked to one of the research directions that I mentioned towards the last part of my presentation, that is to detect, the individual objects within the broader scene of the images that we usually receive from social media, and try to detect object level, damage severity. So I think this is still so right now, if we receive image of a single house or a single object, the models are able to detect damage and severity of the damage. But if an image contains several objects, and the task is to detect those objects and their damage levels, this is something ongoing, and we are working on this. This is still, under research. And so forth.
Okay, thank you.
Thank you very much. Now I have Dr. Moshiri. If you want to ask question, please go ahead. I think you should be able to ask your question now. Maybe in between, Dr. Imran, there is a question on the chat. If you can, or in the Q&A, if you want to also respond to that, I can read it for sure.
Yeah. Okay. Okay. Can you hear me? Or can you, dear
Yes.
Ali?
Yes, we can hear you.
Okay.
Go ahead.
Oh, thanks very much from you, Ali. I enjoyed Mohammed's talk very well, and also regarding of the rating of the Hediya later on. I appreciate it. Was very nice presentation. But I have a question regarding a concept that we called fusion of the soft and hard data. As you mentioned, the expertise play as a role of the soft data, and the image that will be given through, say, satellites, or probably the people who are using the camera, all this stuff, that would be considered as the hard. So there's a good concept that is similar to your concept, that you pay the attention to the role of the human in the loop. The point is this: regarding of the detection more precisely, and to have a more accurate, actually, segmentation among the objects, do you use more classifier rather than the one you use? I mean, did you use a single classifier or multi-classifier? If it is multi-classifier, say you may use support vector machine, naive Bayes, k-mean, c-mean, whatever that we have in the machine learning approaches. I'm wondering whether you have used the different classifier to have the more accurate and precise results. I appreciate it very much if you could just explain a bit.
Yeah, thank you for the question. That's a very valuable question here. So for the segmentation task, so this is the object level detection and segmentation we are talking about. We used 12 state-of-the-art models, 12 state-of-the-art classifiers. And one of the image, I didn't have time to go into the details of those models. Each of those models are, trained on millions of images, and they are super robust in their domains, right? Some are, very good in detecting medical equipment. Some others are very good in detecting flowers and real world generic objects, houses, cups, tea, and spoons, and etc. So we use all those models. There are 12 models that we use, and we were hoping that some of these models will be helpful. Obviously, there are, some models are able to detect some objects, but the majority of the models fail when the object is deformed, when the object is destroyed, right? So I showed you an example of a totally collapsed building. There was a building collapsed on a car, and car was, hid under the collapsed building. So none of those models were able to detect either the building nor the car. So to answer your question, we used all those models, but in the future, our aim is to build a single model that is robust to detect multiple objects of interest. And our objects of interest would be the objects that the emergency response functions are interested in. For example, in the transportation line, those people are interested in maybe vehicles, roads, bridges, etc. And some other, some other department would be interested in only buildings and houses and residential apartments and so on and so on. So our aim is to build single model, but I cannot say at the moment. We may have to develop multiple models, and for each type of object, we may have to develop its own model. So since this is work in progress, I think I will be able to answer this question more thoroughly in the coming months and years.
Thank you very much. I'm mindful of time for those who participants who have time constraint until 1 o'clock here, but there is one question remaining here. I think there could be a short answer to that, and that is about, and that's from Masood, and asking about the time lapse or time that you need to run the model, how long it takes and how effective that would be. Please go ahead.
Sure. So yeah, this is also a very good question. So as I said, the social media data becomes available within seconds of a disaster. And you must have also noticed that in many events, social media actually break those events, right? So Hudson plane crash, the first report of that plane crash came on social media. And there are some other events that actually come on social media before they come to news and other channels. So in that sense, the data is available. Now, how long it takes for our system to deploy and able to extract this data depends on two things. One is we need to determine the strategy to collect data. For example, if something happens, we need to know how we are going to collect data from that region. So there are two modes to collect data. One is if we draw a geographical bounding box around that area where some earthquake happens or maybe some typhoon is hitting and so on and so forth. This is one way to collect. The other way is that if there are some relevant hashtags or keywords that people are using to post relevant images and so on and so forth. So for us, if we collaborate with some local response functions, responders, then they tell us, the set of keywords or the hashtags the local people are using. And that is the only time constraint we have. And that often takes maybe a couple of hours to, obtain and then set our system. So once we have this, either we need to have the bounding box around the impacted area, or we know the keywords. Our system takes input of these keywords and bounding box and then starts collecting data. And once it starts collecting data, the output is available within seconds. So this is there's no latency from the collection to the output. There is only latency from the local responders to give us the relevant hashtags and keywords.
Thank you very much for great answers to those questions. And For the sake of time, I just want I would like to conclude this session first with thanking Dr. Imran for this great presentation, and looking forward to hear more from your research in the future. And also, I would like to thank all the participants, as well as panelists here for today's session. Looking forward to have you in our next session that is going to be in about 2 weeks from now, same time, where we have two other guest speakers looking into other aspects of rapid damage assessment. And with that, thank you very much again, everyone. Have a great day, evening, and afternoon. And again, thank you, Dr. Imran, for being with us today.
Thank you very much.